Hello? Yeah, can you hear me? Yeah, okay, perfect. Okay, so I will start. My name is Carlos Matallana Espinar. I'm the team lead at Protocol Integration Team in Polygon zkEVM. And today we'll be talking about a new data structure, which is the zkBlob, and the data compression in the zkEVM. So what are the parts of this talk? Basically, in the introduction, I will be talking about which is how we put the data availability currently on chain and what are the layer 2 associated transaction costs. Later on, I will introduce this kind of zkBlob data structure, and later on, I will talk about the data compression and all the functionality that we have specified over there. Okay, how in Polygon zkEVM currently looks like the data availability that we put on chain. So we have a smart contract call, which is the sequence batches, and inside this sequence batches smart contract call, we put an array of batches. And what is inside those batches? So we have a bunch of transactions. And those transactions, how are they represented in bytes? So basically what we put is all the transaction data encoding as RLP. Okay? And the signature is concatenated at the very end of this data. This is very convenient to us because inside the zk circuit, we already have this transaction data, the RLP. So it's very easy to hash it, then get the Ethereum signing message, and then perform the easy recover. The trade-off, of course, is that you put a lot of data on chain. And this will be fixed with the data compression. And here, I want to just explain why the cost of a layer 2 transactions comes from. I would say that there are 4 different parts. The first one is the data availability, so you pay for every byte that you put on chain. The second part is the sequencing. When you do the sequencing, you put the data availability, but it also has a constant cost, gas. The third one is the prover. The prover basically is a specialized hardware that you spin up on, well, normally in AWS. And then you take some time in order to compute a proof, and this time when you rent this specialized machine, it's a big machine, then it has a cost associated to it. And the third one is, when you have the proof, you need to verify the proof on chain. So there is a smart contract call, which is the verify batches, and of course this has a cost associated. We will see later on that this cost is very small since we have Stark recursion, and later on we verify the Stark in the Snark, which costs a lot less than instead of verifying a Stark, if you verify a Snark, it costs much less. So basically, those are the numbers. Okay, I just did some measurements, and here I show the Ethereum transfer, ERC20 token transfer, and a swap in Uniswap version 2, which is a quite common Ethereum transactions. And you can see here that 95% of the layer 2 transaction cost goes to data availability. And this is very important. And if you see the third row, the prover, this was the hardware that you rent on AWS. 2 years ago, this cost was very high, okay? And you can see now that it's almost nothing. It's almost negligible. And this is very important, because 2 years ago, a lot of people thought, okay, this is impossible. The layer 2 transaction cost will be very high because in order to run the prover, it takes a lot of time, so you pay a lot of money. And now it's no longer like that. Okay, so we can say that the prover is no longer the bottleneck. This is what we say. So clearly here, the data availability is what we need to reduce. And in order to do that, we're going to use, of course, the EIP 4844 and data compression, okay? Those numbers are not random, okay? They are computed in the following with the slides, but the following with the slides is just about numbers. You can check it. You have a link at the end of the presentation, so you can ask me later on. There are several. This is how to compute the cost of data availability, sequencing, prover, and aggregation, about the ERC20 transfer and the swap of Uniswap. Okay, so how to reduce data availability cost? So first of all, EIP 4844. This basically will introduce these blob transactions in the consensus layer, and from those transactions, basically, it will reduce the gas cost per byte that we put on chain, since it will go to the consensus layer in the blob transaction. And directly, it will cost from 16 gas per byte to 3 gas per byte. Also, the mechanism in order to price those transactions is different from Ethereum, so probably will be a little bit more than this ratio. The ratio is, if I don't remember well, is 5.3x. And also, data compression. Data compression basically is, instead of putting the whole Ethereum transaction on chain, what we're going to put is less bytes, and those small amount of bytes, we're going to apply some custom functionality in order to recover the original Ethereum transaction byte. Okay, so in order to add this EIP for 844, we introduce a new data structure, which is what we call the zkBlob. And this zkBlob would allow to Polygon zkEVM to quickly adapt to the EIP for 844 once it goes to Ethereum. Will happen in Calculate. Also, inside this new blob structure, what we will do is just to verify the polynomial commitment of the blob in order to assure that the data is correct. It allows more things, and I would say that the most important one is that it will allow to us to aggregate all the signatures of all transactions and make a proof in order to check the validity of the signature. So instead of putting on chain 65 bytes of the signature of each Ethereum transaction, it will just be a snark proof, which is a small amount of bytes. Okay? So this snark proof is a little amount of bytes, and the cost of this amount of bytes will be shared among all transactions. And the next cool thing is that we are kind of decoupling this, I would say, data parsing from the data execution. We will see better in the next slide. So this is the current approach, sequence batches. So we have what we call the batch. The batch is in charge of doing all this kind of RLP parsing, easy recover, verify the signatures. Later on, it does the EVM processing. And we switch to this other approach once we have the circuit on the left, it would be the zkBlob, and the circuit on the right will be the batch. You can see that now the batch, it only does the EVM processing. And the circuit on the left, basically, it will take the data in chain, it will do this kind of data decompression in order to recover all the original data on the Ethereum transactions. It will do the encoding of the RLP, it will do the easy recover, and of course, it will verify that the data is correct in the EIP for 844. The cool thing here is like we can remove this kind of computing transaction sign and message and do the easy recover for a snark, as I mentioned before. Okay, let's go to the data compression. Data compression, as I mentioned, we can remove the signature. This basically saves, for each transaction, basically it saves 65 bytes, which is a lot of money. And then we specify a set of functions. It will be, we thought in a, in a protocol in order to apply a small set of functions, very minimal, in order to compress an Ethereum transaction. There are different ways in order to compress data. One of them is doing just like delta states. Another is to apply some well-known libraries on compression. But we took the path to do some kind of custom compression. And for that purpose, we introduced two new, I would say, trees, sparse Merkle tree structure, which is the address tree, and the data tree. Basically, the address tree, it's a sparse Merkle tree, and it's a mapping between an address and an index. The address occupies 20 bytes, and the index, it's incremental. So it will be 0, 1, 2, 3, so you can encode those index in probably 1, 2, or 3 bytes. And the data tree, it does exactly the same as the other tree, but it does a mapping between 32 bytes and an index. So for an Ethereum transactions, instead of putting 20 bytes into the data availability, what you will put is just 1 byte, which will be the index. How to interpret that, we will see in the following slides. And here, basically, it's all the function sets that we define in order to do the data compression. Okay? So we have the first byte. The 3 first bits of this byte defines what function to apply. And then we have the less significant 5 bits, which we call the header payload. So for example, the first one, in order to encode 32 bytes, we just, in the header payload, we put the amount of bytes to read. If you want to code more than 32 bytes, then we put in the header payload the amount of bytes to read, which would be the length of the bytes to read. It's kind of the RLP encoding of the long list. The third one is a small value. If you want to code a small value between 0 and 31, with 5 bits, it's enough. So it is encoded by itself in the header payload. And here comes the two regarding the address, the sparse Merkle tree about the address and the data. Here, the function basically says, okay, what you are going to read is the index. So take that index, goes to the sparse Merkle tree of the data tree or the address tree, and then convert it to 20 bytes or 32 bytes. Okay, so we save a lot of data here. Then, in an Ethereum transaction, there is this kind of value gas price, which is normally it's a value that has normally a lot of zeros. So you can put this value in a different manner, like this floating point thing with mantissa and exponent. So you can encode exactly the same value, but with less bytes. Then you need a way to say, hey, add these 20 bytes, this address, into the data tree. So do this kind of mapping in order to be used later on. So we have this uncompressed address and uncompressed 32 bytes, which basically are in charge to put 20 bytes in the address tree and 20 bytes to the data tree. And the last one, we did a lot of tests of the previous one, and the last one, we realized that when you encode the call data in Solidity, basically, you encode the selector, and later on you encode all the parameters in 32 bytes, but the string and the bytes type are padded to the right until 32 bytes. So we add this in order to save basically all the zeros that we put over there. This is very important to say also that some of these functionalities, when you apply those functions inside the data field of an Ethereum transaction, we pad them to the left 32 bytes in order to fit the call data, the API encoding basically. Okay, so let's see an example. This is an ERC20 token transfer with all the fields. This is what we are putting right now on chain, which is basically the RLP of all transaction fields. And this is what we are going to put thanks to this data compression. Okay. You can ping me afterwards so I can explain byte by byte. But basically, we are reducing a lot. And the field that we are reducing a lot is basically the to and the data, okay? Because it contains some addresses. So we put, instead of 20 bytes, just 1 byte, which is the index of the address tree. So what is the gain? What is the gain? If we apply data compression, the Ethereum 20 transfer, the gain is about 7.5x, the ERC20 token transfer as well, and the swap on Uniswap, it's about 10x. So we save a lot. We save a lot over there. And thanks to the EIP 4844, we perform a 5x over there, at least. I would say that this, regarding the EIP 4844, it's a very conservative number. And how it will end. This is exactly the same table that I put at the very beginning. So we can see here that the data availability cost is reduced dramatically. Okay, it is reduced a lot. So instead of going to a few cents, you are going to $0.0064 in the case of Ethereum transfer. So we can say that the final values over here, I mean, we are reducing a lot of data compression. Okay, and for the user, basically the user will benefit from that. Okay. And that's it. This is the link of the slides. If you want to share, if you want to check all the numbers in order to get all the values that I shared at the very beginning, and you can ask me afterwards if you want. Thank you. I don't know if we have time for questions. 1 minute. 1 minute. One question. No. Yeah, over there.
Hello. Yeah. Just very quick question. How many blocks or transactions did you test your numbers when you showed 7x and all that? How much data did you use for the experiments?
How much data? I mean, this is,
here.
I would say this is a standard Ethereum transfer.
Yep.
I mean, if you take an Ethereum transfer, the data of an Ethereum transfer, and then you reduce it, basically this is, we are from the 111 bytes, if you take 65 less, which is the signature, and then you reduce the 2 from 20 bytes to 1, then you get this 15.
All right. Thank you.
You're welcome. Yep. Okay. Thank you.
Thank you, guys.